In this chapter, we will be studying polynomials and factoring. In this lesson, we will be looking at special products or special factoring. To begin, we'll look at the difference of squares.
Okay, so in this lesson here, what we're going to do is we're going to talk about a couple of different patterns in factoring that are what we would call special products, like you say up here. What they are is they're just little patterns that you should recognize that are a little different than the ones that we've just been working on, but important nonetheless here. So we're going to start with this one called the difference of squares. This one comes up so often. I mean, if there's ever a case of you got a question on an exam and your teacher wants to make it just a little bit more difficult, but not too much more difficult, throwing in a difference of squares is a great way to do that. Now, I'm going to zoom in here, and then I want to show you a little pattern here and just talk to you about kind of where this comes from here. If I gave you, for example, x plus 3 and told you to square it, one of the mistakes that people make right away is they go, that's just x squared plus 9. You just square both terms there. And that's not true. Okay? That is not true. That's not the way that works. X plus 3 squared looks like this. It's x plus 3 multiplied by x plus 3. And then every term here in this binomial gets distributed to every term here in this binomial. And when you do that, you'll get x squared plus 3x, and then we start with the 3 there, plus 3x plus 9. And so what we get here, this middle term, becomes x squared plus 6x plus 9. You get that middle term there, okay? That's what happens when you square a binomial. And actually, we're going to come and talk about this in just a few minutes, okay? It's a perfect square trinomial. This pattern that people are constantly trying to yank out of that actually doesn't happen as a result of the x plus 3 being squared. Okay? What happens here is when we multiply these two together, these x minus 3, x plus 3. Now notice the difference between them. This has got the negative sign in between, this has got an addition in between. We call these conjugates. Okay, specifically we will call these binomial conjugates. Okay, now let's take a look at what happens when you multiply conjugates together. And bear in mind, okay, this is different. That we are not squaring a binomial. We're multiplying two different binomials together, just binomials that are related. And so when you do this, you would take that first term from that first binomial and you would distribute it to both terms here. So it's going to be x squared plus 3x. And then we'll take the negative 3 and distribute it through. So we're going to get negative 3x minus 9. Now, look at what happens here. This positive 3x and the negative 3x, they are essentially these inverses of each other, these additive inverses of each other. They cancel each other out, and we're left with x squared minus 9. And this is a difference of squares. Now, if we wanted to now factor this out, what happens here is you have to look at this pattern here and recognize what's going on here. When I multiplied those two conjugates together, I got x squared minus 9, which means if I start with x squared minus 9 and I want to factor it, I'm going to factor it into a pair of binomials here, and I recognize what that's going to be because I've got a square, a perfect square, minus a perfect square. So my result here will be x minus 3 multiplied by x plus 3. So I'm going to go right back to this initial stage here. And you should know that in math, a lot of ideas that look like someone was really, really clever and you got to be super smart, like to see that x squared minus 9 becomes this. I mean, that would be a real jump in intelligence there, of an idea there. Like that's a huge step here. But recognize that's not how it happened. What happened was somebody was expanding something like this out and notice it got to here. So then the obvious backward step is to go from there to there. Like it's not that creative to simply go backwards here. Now, but the trick is for us to apply that sort of thinking consistently. So what we're looking for here is we're looking for the difference of squares. Two perfect square terms with a subtraction in between. If there's an addition in between, it's a dead end. There's nothing that you can do there, okay? So let's take a quick look down here at this example. When you've got x squared minus, 16x squared minus 25y squared, okay? This is a perfect square. This is a perfect square. The square root of 16x squared is going to be 4x. The square root of 25y squared is 5y. So then my two factors become 4x plus 5y, 4x minus 5y. Where this is going to get difficult for people is simply recognizing whether that's a perfect square or not. Like you're going to have to spend a little bit of time getting comfortable with what those perfect square numbers are. Okay, the more comfortable you are identifying those when you see them, the better. And again, remember, x squared, 16x squared plus 25y squared. That is as simple as that's going to get. That's done. This is not a difference of squares. This is a sum of squares, and you can't factor that. Anyway, let's take a look at some examples here. Hopefully you'll get a real good sense of the pattern in just a second. Okay, so we're just going to factor a bunch of these. So here we go. X squared minus 81. Well, okay, I know that this is going to break apart into two binomials multiplied together. X squared is a perfect square, and its square root is x. Okay, I can split that apart into x multiplied by x here. Now, 81, what's the square root of 81? 9. So I'm going to put a 9 here and a 9 here, and then because this is a difference of squares, I'm going to have different signs there, so I've got the two conjugates multiplied together. So there we go, x minus 9, x plus 9. Okay, 16a squared minus 49b squared. You know, it doesn't matter to me how complicated those terms get as long as I recognize that those are both perfect squares. So I'm going to break this into two binomials. The square root of 16a squared, well, the square root of 16 is 4. The square root of a squared is a. So I'm going to start with 4a in both of those. The square root of 49b squared, well, the square root of 49 is 7. The square root of b squared is b. And so, again, to get that difference of squares to pop out, we make this a negative and we make that a positive. There's my conjugates. Now here, notice that 3 isn't a perfect square, neither is 12. But both of those are divisible by 3, so I can take a 3 out. And then notice that I've also got an a in both those terms, so I can take that out. And when I do, I'm left with an a squared minus 4b squared. Now, you always have to investigate what you're left over with once you've taken out a common factor. And notice that right there, two terms multiplied together, sorry, two terms, it's the difference between them, and there I've got a perfect square minus a perfect square. I need to keep going. Now I should always be looking for that. Now that 3a doesn't go away. I still write that because it's still part of the overall expression here. When I'm done, my result should be equal to what I started with here. The square root of a squared is a, so I put an a there. The square root of 4b squared will be 2b. And then again, because it's a difference of squares, I throw in my binomial conjugates. So this will be 3a multiplied by a minus 2b, a plus 2b. Okay, now, negative 9x squared plus 25. Okay, well, this is not exactly pretty. Having that negative out front there, like that, is a little awkward here. What I'm going to do actually to make this look a little bit better, I'm going to take that negative out. So I'm still going from the highest degree term to the lowest degree term, but I took out a negative out of both those terms. So I get negative 9x squared minus 25. Now, having that negative out front of a set of parentheses out front of the whole thing, that actually doesn't look nearly as harsh as it does having that negative inside there. And pulling that negative out to leave me with this is actually a little bit easier. Now, the other thing I could have done is change the order of those terms, made it 25 minus 9x squared. But that actually looks even a little bit more awkward. This is a lot better here. So negative, now this is going to break apart into a difference of squares because the square root of 9x squared will be 3x. 3x. Then the square root of 25 is 5. And then because it's a difference of squares, I put a minus sign there and a plus sign there. So there, those are my conjugates. Here, don't fall into this little trap here. This is a sum of squares. That's it. That's done. That is not going to get any simpler than that unless there was something common to both those terms, and there isn't. So that's as far as we're going to go. Okay? And it's totally okay for that to happen, by the way. Don't feel obliged to try to factor that if it can't be factored. That's just a test. You're done. Over here, okay. This is a little less obvious, okay? But when you've got something to the fourth power, bear in mind that x squared squared is x to the fourth. So these still are differences of squares. This is a difference of squares. It's just a little harder to see. But the square root of x to the fourth is x squared, and the square root of y to the fourth is y squared. And then it's a difference of squares, so I'm going to put my subtraction and my addition in there. But before I leave this, I notice, well, wait a minute, whoa. This can be broken down. Now, x squared plus y squared can't, but x squared minus y squared can. That is also a difference of squares. So I'm going to break that one apart into two, and then this last one here I can't. It's a sum of squares, so that's as good as that's going to get here. But this one here, the square root of x squared is x. The square root of y squared is y. This little guy right here is a difference of squares. This becomes negative and positive in there. So it's a little bit more factoring. This is what we would call a nested difference of squares. Because after your first little bit of factoring, there's another one that's kind of sitting inside or nested inside that factoring. Okay, good. Let's keep going. Just a few more here. Whoops. All right. 4x squared minus 64. Okay, now this is a difference of squares just the way it sits here. However, there's a common 4 here that I can take out. It would probably be smarter to take that out first. And when you divide 64 by 4, you're going to get 16 here. Now, this is still a difference of squares. So even after I took out what's common, I've still got a difference of squares here. So that'll break apart into two binomials. X squared can be written as x multiplied by x. 16 is 4 multiplied by 4. And then because this is a difference of squares, I'm going to put a negative there and an addition there. And there you can see my binomial conjugates. Okay, now let's take a look at this one right here. 9x to the 6th minus y to the 8th. Okay, now it might not be obvious right off the top here that this is actually a difference of squares, but in fact it is. Okay, 9 obviously breaks down into 3 and 3. That's not the issue here. Now let's just think about this. What would the square root of x to the 6th be? Now, if you remember here that a square root would be the same as x to the 6th all to the 1/2. Just think about this. What is 1/2 of 6 when you multiply the through? And the answer is it's going to be 3. So the square root here would be x cubed. And then by that same logic, we can figure out what the square root of y to the 8th is, and it's going to be y to the 4th. So minus y to the 4th plus y to the 4th. So we've created the conjugate here by having same term here, or the same two terms here, subtracted here and added here. Now, can we go further with this? Is this one here a difference of squares? No, it's not, so this is a good place to stop. Okay, let's take a look at this one. Okay, now before we do anything here, it looks like we got a little bit that's common here. There's a common factor of 2 between these two terms here. Then there's an r that's common to both. And when we take that out, we're going to be left with x to the 4th minus 36y to the 4th. Okay, and now again, we recognize that this is a difference of squares because, okay, we can break this down into two binomials here. Remember that the square root of x to the 4th, and we looked at this before, is going to be x squared. So I put x squared there and there. The square root of 36 is going to be 6. And then the square root of y to the 4th will be y squared. And then again, because these are supposed to be the binomial conjugates, this will be subtraction, this will be addition. Now, I would love to jump and make this into a difference of squares, but the truth is that 6 stops me from doing that nice and cleanly here, okay? Because you can't take the square root of 6, at least not nicely. So this is where we're going to stop right here. That's going to be fine. Over here, what I would do with this one here first, actually, and this might seem a little goofy here, but this fraction in here, I mean, I can factor around this. I mean, I totally could. But this fraction here makes things a little bit more awkward to work with. So what I want to do here is I'm going to get rid of it. I'm going to get rid of it by dividing out that 1/9. Now I recognize that this might not seem like the most direct thing to do, and I'll show you the other way of handling this here in just a second here. But what I want to do here is I want to factor that out here. So 121, if you divide by 1/9 here, it's going to be the same as multiplying by 9. So it's going to be 1089 x squared minus y squared. Now, I do have a really good motivation for yanking out that 1/9 is a common denominator, as a common fraction here, or factor here. But taking out the fraction when I can is always a good idea here. Now, this is a difference of squares. Now, it's not obviously a difference of squares. Okay, I'll give you that. That's not really all that clear, but the truth is it is. The square root of 1089 is going to be 33. And then the square root of x squared is just x. And the square root of y squared is going to be just y. And I make this these conjugates by putting the subtraction and the addition here. Now, that is one way of doing it. And actually, that's not a bad way to do it at all. That's a pretty good way. You could, however, just jump into this and make this a difference of squares by taking the square root of 121x squared, which would be 11x. The square root of 1/9 y squared would be 1/3 y, 1/3 y. And again, make it a difference of squares, or binomial conjugates, by putting the subtraction here and addition here. Okay. Over here, I'm not particularly fond of the way this is written. Okay, I don't like the fact that it's written in this order, so I'm going to factor a -4 out of that, because I can see that that's common. 4 is common to both. I want the negative out here, so -4. Whoops. That's going to leave me with, and I'm going to change the order here, 25x squared minus 1. Okay? That is just a much nicer order. It's cleaner to me. It's clear what's going on. And I can see right away that that's a difference of squares. The square root of 25x squared will be 5x, so I put 5x there and there. The square root of 1 is 1, so that's easy. I put that there and there. And then to make the binomial conjugates, I'll put the negative there and an addition there. And now finally, in this little section of questions here, 27m cubed minus 12m. There is a common factor of 3 between 27 and 12, so 3. And then I can see that there's a common m to both of those, so I'll take that out here. That's going to leave me with 9m squared minus 4. And I see from here that that's a difference of squares. Okay, the square root of 9m squared will be 3m. The square root of 4 will be 2. And again, to make these binomial conjugates, I'll put a subtraction there and an addition there. And there you go. Very similar sort of pattern every time, but I have to identify very clearly when it's a difference of squares. And again, remember to take out what's common first. It's got to be subtraction in between in order to make this a difference of squares. Anyway, there you go.
And now we'll look at perfect square trinomials.
Okay, so here's the other special little bit of factoring here that we want to look at. These are the perfect square trinomials. Okay? This is how we handle when we have a binomial here that we're squaring, okay? The 2x squared plus 3. So when you do that, when you have that squared, remember this is not equal to, right? You don't just jump into this and make this 4x squared plus 9. That's not what you, in fact, let's zoom in a little bit on this. That is not what you do here. What you do with 2x squared plus 3, 2x plus 3 all squared is you write that out twice. 2x squared plus 3 multiplied by 2x plus 3. Sorry, I think I said 2x squared plus 3. 2x plus 3 multiplied by 2x plus 3. And then when you distribute each term here to every term here, you're going to get this guy right here. Now, what's interesting is every time you do this, that middle term there gets doubled. Now, in the past year, you'll recognize that every time we've done this, we've added the two middle terms together. In this particular circumstance here, those middle terms will be identical. Tell you what, let's approach this a little differently. Let's say it was just a plus b squared. So this would be a plus b multiplied by a plus b. Now, I will distribute that a through both of those terms. So this will be a squared plus ab. Now I'll distribute the b through both those terms, and I will get ab plus b squared. And again, notice that that AB term, that middle term, there are two of them. So we simplify this down by making this plus 2AB. So there should always be a factor of 2 as part of that middle term here. Now, just really quickly here, if this was a minus b squared, then what you would have noticed here, you'd get a squared, and it would be, the two middle terms would be negative, and that final term would also be positive again, because a negative multiplied by a negative number multiplied by itself would be positive. And so you'll end up with this negative 2ab here. So now the trick is to recognize this pattern of perfect square, and then 2 times the square roots multiplied together. That can be taken back and in factored form is going to look like these guys right here. Okay? So this is a little hard to recognize. You really got to be paying attention, got to be looking for it to see this one and to take advantage of this little shortcut. Let's do some examples. All right, so we're going to factor each of these here. Let's maybe zoom in just a little bit. Okay, so here we go. X squared plus 12x plus 36. Now, what I recognize here is the square root, okay, the square root of x squared is x, and I notice that there's a perfect square over here. The square root of 36 is 6. Now, the way the pattern works for these perfect square trinomials is if you now multiply these two together, so 6 times x is 6x, and multiply by 2, do I get the middle term here? Yes, I do, 12x. So this thing here must be x plus 6 squared. Okay, that's the pattern that we've established. Square root, and if when I multiply these two together and multiply by 2, do I get the middle term? Then that is a perfect square trinomial. Take a look at this guy right here. Okay, 9x squared is a perfect square. Its square root is 3x. 1 is a perfect square. Its square root is 1. Now, 3x times 1 is 3x. If you multiply that by 2, you get 6x. So there it is. The answer to this is going to be 3x plus 1 all squared. Okay, take a look at the next one. 4x squared minus 20xy plus 25y squared. Okay, now, notice that that first term is a perfect square. The square root of 4x squared is 2x. The square root of 25y squared is 5y. Now, 2x times 5y is going to be 10xy. Multiplied by 2 is 20xy. But now notice there's a negative here. Now, but I showed you an example of that just a couple seconds ago. That simply means that it was negative in between here. So 2x minus 5y squared. And this one right here. Now, before we do this one right here, I'm going to rewrite this one. I don't like the order that it's written in. I'm going to make this thing look pretty. There we go. Standard form looks a lot better. Now this is easier for me to work with. 16x squared, the square root of that is going to be 4x. 9 is 3 squared. Now, 4x times 3 is 12x. Multiply that by 2. Yes, I do. I get 24. So this has got to be 4x plus 3 squared. And now finally in this little section here, okay, first of all, I notice that there's negatives everywhere. There's also x's in every term here. There's got to be a common factor. And between 3, 18, and 27, there is a common factor of 3. So I'm going to take out a negative 3x. I'm going to take out the smallest exponent, so that's the squared. That is going to leave me with here x squared plus 6x plus 9. Okay, so now I can't get around the fact that there's that negative 3x squared that's part of this answer here. So negative 3x squared. Now, square root of x squared is x. The square root of 9 is 3. X times 3 is 3x. Multiplied by 2, does that get me 6? Yes, it does. So this right here can factor down to x plus 3 as long as I put a square up top there. And that's the answer that I'm looking for.